So last time we talked about data centers primarily. In this session, we want to talk more about what AI is and how it's currently being used. So I wanted to start that by giving an overview of how AI works and how that leads to some of its flaws that there are many, but these are three that have gotten a lot of attention. And so once we see how it works, it will be obvious why they're so hard to fix. So to talk about AI, it's important to put it in historical context. AI is something that we've been hearing about our whole lives. Every 10 or 15 years, some company will say they've come up with something that they consider intelligent. And going back to the 50s, this was mazes. The chief problem at the time was trying to solve mazes like this. And somebody had come up with a program that could do that. It could walk through the maze. It could figure out where it had been before. It could remember not to backtrack. And so they could show it a brand new maze like this, and within a few seconds, it could show what the path was. And so people were very impressed by that. People said, that kind of does look like intelligence. And so a lot of people thought, okay, that is one of the first concrete steps we've taken towards artificial intelligence. But then the skeptics started looking at it and said, actually, the way that you did this doesn't look like it would work if you started using larger mazes. The number of combinations is going to explode. We just don't really think this is a true solution. So why don't you try to solve this maze? And it couldn't do it. The program wandered around aimlessly. It got stuck in corners, never got anywhere. So they said, okay, that's actually not intelligence. And then in the 70s, it was checkers. And it was pretty easy to write a program that played checkers. But what was unique about this is that it actually learned from experience. As it played, it got better. It had ways of adjusting its strategy based on whether it was winning or losing. And so people saw that and thought, that kind of looks like intelligence too. And it played everybody on the team, beat everyone. So they said, okay, let's maybe enter this in competitions. Started winning all of those, so it could beat everyone. And then they took it to the state championship in Cincinnati. And it took on the state champion and lost. And no matter how much they tried to play better players, it never got any better than that. So it got almost as good as the state champion, but could never improve. So people said, well, that can't really be it then. So then in the early 80s, a group of mathematicians said, hang on. Here we've got an equation that we can mathematically prove can learn anything given enough examples. And so to demonstrate that, what we'll do is give it a lot of examples of our handwritten numbers. And now we can just write a set of numbers on a piece of paper and run the program against it. And it got all of them right. And people said, that's pretty cool. That actually looks like it's intelligent. Let me try. So people would write their own numbers. And it was terrible. Got half of them wrong at least. And so the mathematician said, well, okay, the reason is it's only learned from our examples. So anybody that wants to use this, give us 10 samples of handwritten digits for each number, and we guarantee this will work. And so people said, no, we're not going to do that. And the first one, though, that really got a lot of hype, as this really is artificial intelligence, this is something that looks smart, was when IBM's Deep Blue played Garry Kasparov, who was the world champion at chess at the time. And people had always said, if a computer can learn to play chess, that probably does represent intelligence. So that was very hyped up by IBM themselves. They were spending a lot of airtime telling people what an intelligent machine they had. And so when the tournament came, they played Kasparov, and they won. They had defeated the world champion, and everybody looked at that and said, wow, that really does look like intelligence. But then the skeptics started looking at that, and They said, you know, this actually doesn't seem quite as impressive. Because for one thing, IBM knew that there was a lot riding on this. And so, because they would get a lot of publicity if it worked. And what they found is IBM had been kind of underhanded in the way they played. You're supposed to give your chess opponents all of your historical games to learn against. And they refused to do that. They were making changes to the game mid-play, which people thought was kind of sketchy. So the skeptics said, okay, show us the program, show us how it works. And IBM refused to do that. They decommissioned it, deleted it, wouldn't let anybody see it. So people said, all right, well, we can probably figure out what you did. We'll reverse engineer this. What we think you did was you took a mediocre chess player and ran it at 200 million moves per second that it could analyze. And so it's not really intelligence, it's just a faster calculator. And so IBM, if you really think you've got an intelligent machine, try playing a game that has more combinations where that approach won't work. Try playing the game of Go, where there are hundreds of potential moves each time. And so IBM tried, couldn't do it. Nobody could do it. Nobody could build a game that played Go effectively. So, not artificial intelligence. And in the early 20-teens, the problem was trying to classify images. So taking a set of pictures and saying which of these are dogs and which are cats, for example. And it was something that programs were really struggling with. They had this running competition for 7 years. Nobody had made any significant progress. They were getting about a quarter of them wrong. And just nobody had any ideas for how to proceed, for how to make them any better. So one team said, hang on, let's go back to this handwriting idea. They said they had an equation that they guaranteed could learn anything with enough examples. But that was in the early days of the internet, when they didn't have a lot of data. Now we've got tons of it. So let's take that equation, which is called a neural network, and let's give it 10,000 pictures of dogs, 10,000 pictures of cats, and see if it learns to tell the difference. And it did. It worked amazingly well. It worked so well that within 2 years, they ended the competition because the program could classify images better than the human judges. So the skeptics came out again, and they said, all right, let us take a look at your program. And they said, sure, here you go. And the skeptic said, this is just a math equation. We don't really know what to make of this. But okay, if you think this is intelligent, try playing chess. And so they took 2 neural networks and had them play each other, about 50 million games, knowing nothing but the rules, but learning by playing each other. And so people said, all right, if you think that's going to work, the successor to Deep Blue was Stockfish at the time. It was the best computer program that had ever been written. It could easily beat any human. So they said, all right, try playing Stockfish. And they did and completely destroyed it, 28-0. So now this had people's attention because this was the first thing that was not only looked like intelligence, but worked in multiple domains. But people were still a little skeptical because it was just a math equation. They didn't really know what the capabilities were, so they said, all right, try to play Go. Nobody's ever been able to do that. And so they they had 2 neural networks play each other, played 100 million games over 9 hours, and not only did it learn how to play Go, it beat the world champion. And so at that point, that had a lot of people's attention. So they started looking at handwriting. It turns out you don't need 10 examples from everyone. You need 1 million examples overall, and you can learn to read anyone's handwriting, so that was easy. Checkers, by that time, checkers programs were so good they didn't make any mistakes. So it was impossible to really beat one, but they trained a neural network to play checkers, and it also got so good it didn't make mistakes, so they just constantly tied each other. But no human could compete with either one. So that was another thing that neural networks were able to do that nothing else had been able to. Mazes, they actually couldn't do. So they trained the neural network and gave it 10,000 mazes, and it said, yeah, I know what the objective is. You want me to find a line that connects these two, but that doesn't tell me how to do it. So I can't learn that from examples. So in 2017, the transformer was invented. And that's what we had said last time opened the door to ChatGPT, because the transformer allowed an entire conversation to be held in memory at one time. So they put a transformer on the neural network, and it was able to pull the entire maze into memory at one time. And it said, okay, you want a path? Here's the path. And so by 2017, this combination of neural networks and transformers had solved every problem that AI had not been able to solve in the past 7 decades. So at that point, every single tech company was looking at this equation and saying, with the combination of neural networks and transformers, what data do we have access to? How much energy can we procure? And how large an AI can we build? So every tech company was going about this in a different way. I think it's worth looking at the OpenAI and ChatGPT example because people are familiar with that, and because that's been the most successful so far. So I'll skip over exactly how it works, but effectively, you end up with what's been called autocomplete on steroids. It was called that last time by one of the speakers, and I think that's a good way to think about it. That is almost exactly what it's doing. It is looking at what's been written so far and trying to make a prediction for what the most likely continuation is. And the reason that you can make a chatbot from that is you can give it text that sets the context for it. And so if you ask a chatbot, what is the capital of California, it will see it as this. It will read this part first to set the context. This is supposed to be a conversation with a friendly, helpful chatbot. And it will predict, okay, what is the most likely thing that a chatbot would say in this context? And so it will be very easy for it to get that right. So that's why these things that are just autocomplete can still be used to do some pretty impressive things. One thing, though, I don't like about the idea of calling it autocomplete is it's easy to take from that it doesn't have much capability, because we know autocomplete is not that great. Autocomplete on your phones is something completely different, though. That's just looking at a list of common phrases and trying to match them. When you take autocomplete and connect that to a neural network and a transformer, it can now complete sentences like this one. So there's a lot of question as to how much of this is hype, and I think there's a lot of hype. These tech companies are all in competition to see who can build the largest one, so they're exaggerating the capabilities. They are underestimating timelines. They're trying to get as much funding as possible for these systems. So they are definitely overhyping what they can provide. But the underlying technology itself is not hype. Neural networks and transformers are an extremely powerful technology. And in the wrong hands, this is very dangerous. So if we look at what a chatbot is, it's not much more than the autocomplete, but they do have to give it an objective. They have to essentially teach it how to be a chatbot. So they use reinforcement learning for that. And that is essentially giving examples of how to behave. So these are examples of this is what a friendly, helpful response would look like. And then at that point, it's an unfiltered chatbot, though. If you were to ask it to write a computer virus for you, it would do that. So they have one more layer on top of that called the policy layer, and this is a set of rules. that that are intended to guide its responses. So these are things like don't tell people how to create dangerous weapons, don't participate in conversations about self-harm, things like that. And that's it. Those three pieces are what make up ChatGPT. And so for a lot of the examples of chatbots that are starting to be used to make serious decisions, this is all they are, is autocomplete with these thin layers around them. And so it does have some pretty impressive capabilities. If you look at ChatGPT 5, it can do all of these seemingly amazing things. But the reason is, you can think of it as an expert in language, as an expert in that one thing. It's read the entire internet, and it has learned very well how to extract meaning from sequences of text. And so in that context, these capabilities make sense. If you can speak every language perfectly, then translation becomes easy. If you can speak legalese, and you've read all of case law, then you can pass the bar exam. If you know medical terminology and you've read all the research papers, then you can ace all the licensing exams. Math, science, and programming are all just structured symbolic languages. So it can do these things extremely well, but that's essentially all it can do. All it can do is language-based tasks. But it does have some very significant flaws that are really important to take into account as this starts to be deployed and starts to make real decisions that affect people's lives. And one of those is hallucinations. So hallucinations happen because it is autocomplete. It was not designed to make truthful or factual statements. It was designed to predict likely answers. And so you can see how that can go wrong. If you have a simple question like this, what is the capital of California? Then the most likely response, when it first looks at this, is, well, typically somebody would answer this by saying the capital of California is. And when it tries to come up with the next word, it's going to have seen thousands of examples of that. And they're all the same one, so it's going to say, by far the most likely answer is this. And it's going to be right. And so people are going to look at that and say, this is amazing. But if you ask it something that's out of left field like this, then it's going to do the same thing. It's going to say, okay, typically somebody would answer like this, and when it gets to the next word, there's not going to be anything that's obviously the most likely. So maybe it's going to say Hawaii, maybe it's going to say Honolulu. In this case, it says Atlantis, because why not? And so at this point, though, that becomes part of the chat history. So anything it says after that has to justify that. And so it just starts making up nonsense. So the way they try to deal with that is something called grounding, and you can kind of think of it as maybe a Google search, where it recognizes it's about to make a statement that is factual, and so it checks to see if that's correct. And it works somewhat. The first ChatGPT 3 had a hallucination rate of maybe 40%, and now they're down to 1 or 2% with grounding. But I wouldn't call it a solved problem, because if a chatbot is being used to make important decisions, 1 or 2% of the time making up nonsense, I think, is not acceptable. And I think also you have to consider where the grounding is coming from. We can all agree on the truth of things like state capitals, but other things there is some disagreement about. And so I think it's important to know who it is that's providing what's considered the source of truth for these. Another issue with these is harmful output. Things like writing computer viruses, and they try to handle a little bit of that in the reinforcement layer by giving examples of people asking for information on making weapons and giving examples of saying no. But you can't anticipate everything somebody's going to ask. So the policy layer has rules to say don't do that. But these are notoriously fragile. When a model comes out, within minutes, people have published ways of getting around those guardrails. And so everybody is coming around to the idea that this is not going to be sufficient, but nobody really has a solution for it yet. So this is very much an unsolved problem. And bias. Bias exists in all three of the layers. And it's pretty obvious why. The internet itself is biased. And all it's done is read the internet and incorporated everything in it. Somebody in the last session made the point that the Global South was likely to be most impacted by this. And I think that's right. And one example of that is that in the internet data, all of that information was produced by people who have internet connections. So people from the Global South don't really have a voice that has even been heard by these large language models. And so their views are not going to be represented in the kind of output it generates. Same thing with reinforcement learning. Anybody who is modeling behavior for it to emulate is going to have their own bias. Anybody who's creating rules for it to follow is going to have their own bias. Personally, I think the only way to deal with this is to bring all of this under democratic control so that people are making the decisions for what data it's trained on, what kinds of behaviors it's given as examples, and what kind of rules it needs to follow. Because all of us are going to be impacted by this technology. And right now, it's only the tech companies who are deciding how these things work and how they behave. So now I want to turn it over to Raj to give some more of the history from the perspective of a machine learning engineer. Thanks.